velocity means distance by time taken. So time means velocity divided by distance. Galvanometer is the one which is used to measure the presence and direction of the current. Okay, so galvanometer, the measuring instrument of the current. Subtraction of the total current with respect to the current which is flowing through the galvanometer gives you the amount of current which is flowing through this resistor. In voltmeter, you connect the resistance in series with the galvanometer, and that resistance is said to be very high. Hello everyone, I'm Runda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to Session 5 of Chapter 4, Moving Charges and Magnetism. In today's class, we are dealing with something more about the moving charges magnetism concept, and that is nothing but magnetic dipole moment of a revolving electrons, or it is also called as magneton, which is very important derivation. So you all know that there is a magnetic moment in case of the electrons. The electrons exhibits certain magnetic dipole moment. So let us get into it. What exactly is going on here? As you all know, that is, there is a nucleus with the charge, positive charge, wherein the electrons is revolving around a positive charge of the nucleus, that is electrons, and the electron sign is said to be negative. Okay, so now you know this condition, and the electron is revolving around the nucleus with the radius r. And you also know that charge constitutes for the electric current, that is current I. How do you get the existence of the current? It is due to the charges moving with respect to time. So how can you call this charge Q as? Charge Q is considered to be the electrons which is moving, and the magnitude of electrons is being considered over here. So you have I is equal to E divided by T. And as you all know, E means the electron is revolving around the nucleus, that is the positively charged nucleus. So the revolution can be given as, that is period of revolution. Revolution period is given by T, this T, okay. So you can just consider T is equal to the circumference, okay. That means velocity means distance by time taken. So time means velocity divided by distance. So what is the velocity to cover over here? So velocity is equal to distance by time taken. So now you have got T, you will have to check out T. So what it will be? It will be distance by velocity, and distance is nothing but it is the circumference through which the electron is traveling. So we can give the circumference of the circle as 2 pi r divided by v. So we know that T is equal to 2 pi r divided by v. So substitute in equation 1. On substituting the value for T in equation 1, we have I is equal to, you have E divided by 2 pi r divided by v. This v goes to the numerator, so you can write it as v over here. So you have EV divided by 2 pi r. So this is the concept of I in case of the revolution of the electrons around the nucleus. So now we introduce a concept, that is a magnetic dipole moment of an electron can be given as nu and L. The magnetic dipole moment of an electron is given as the product of current as well as the area. Nu L is equal to I into A. When this concept is introduced, you have to substitute what is I, EV divided by 2 pi r, and A is nothing but the area. Area of a circle is given by pi r square, for which pi gets cancelled with pi and r gets cancelled with square. So you're left out with nu L is equal to EV divided by 2, and here remains the r, EVR divided by 2. So we can correlate for the angular momentum. So what is meant by angular momentum? We know that L is equal to mVr. We have VR, we don't have m. So what do? We just multiply and divide with mass of the electron, that is m subscript e. So on multiplying and dividing with m subscript e, that means mass of the electron, you have towards your right hand side, we can get it as nu L is equal to m e v r, and e divided by 2me. So this equation can be written as E into L divided by 2me, and this is nu L. Okay, so this can be called as magnetic dipole moment of an electron, and it can be taken as nu L is equal to minus E divided by 2me into L. And the negative sign indicates that the magnetic moment as well as the angular momentum both are acting in the opposite direction, this negative symbol. Then, so the gyromagnetic ratio can be given as nu L divided by L is equal to E divided by 2me. This concept is called as gyromagnetic ratio of the electron. So now, the value for this is said to be constant, and it is given as 8.8 into 10 raised to 6 coulomb kg inverse. This is called as the constant value for gyromagnetic ratio, this concept. And now, we know that the concept according to Bohr's atomic model, the complete concept goes out to be according to the Bohr's atomic model condition, by which it is called as Bohr-Magneton also for this derivation. So according to Bohr's atomic condition, we have three postulates. Out of that, we take the postulate that is angular momentum is equal to integral multiples of h by 2 pi. That is, we know that angular momentum is equal to integral multiples of h divided by 2 pi. So substitute the equation for this. We have nu L is equal to E divided by 2me, and you have n into h divided by 2 pi. So how can you rewrite? Nu L is equal to NEH divided by 2 times it is 4 pi me. And you know that if suppose n is equal to 1, you can rewrite nu L is equal to EH divided by 4 pi m, which is known as, that is, the magnetic moment is also known as Bohr-Magneton. So nu B is equal to nu L, which is also equal to nu S. The value can be called as 9.27 into 10 raised to minus 24 am square. So this is the value of the Bohr-Magneton, that a constant value for all these equations which we have derived over here. So that is all about this, the magnetic dipole moment of a revolving electrons, which is also called as Bohr-Magneton, which is a very, very important derivation from this chapter. So I hope you are clear. First of all, you will have to draw this diagram, give some description, that is, an electron is revolving around the positively charged nucleus with certain radius r. That is the description what you have to write, and then you have to start up with the charge, that is current is equal to charge per unit time, and then you have to start step by step, and finally you have to end up by equating for the Bohr-Magneton, wherein you will have to even give the gyrometric ratio form as well. So this is all about this derivation. Next we are going on to moving coil galvanometer. So what is meant by a galvanometer? Galvanometer is the instrument which is used to measure the presence of current, that is the direction of the current. So galvanometer is the one which is used to measure the presence and direction of the current. Okay, so galvanometer, the measuring instrument of the current. Okay, so now having this, there is a deflection. How exactly you read the galvanometer? You know, in a galvanometer, you have certain division. For example, if there are certain divisions from here to here, the same number of divisions also is present at the other side as well. If there are 30 divisions here, there are 30 divisions here. That means the deflections shows the presence of current. That is how much amount of current is present over there in the galvanometer, which you'll be doing in the figure of merit of galvanometer in your practical exams. That is, 1 degree of deflection gives you certain amount of current. That is the concept. So it is shown by an angle to what extent it is been deviated, deflected, and that is given by theta. Theta gives the deflection of the galvanometer, which shows the how much amount of current is present that instrument, that is galvanometer. Having this concept in your chapter moving charges and magnetism, we are dealing with two types, that is conversion of galvanometer into ammeter and conversion of galvanometer into voltmeter. There are two concepts. How do you convert a galvanometer into ammeter? How do you convert a galvanometer to voltmeter? This is a concept what you have to study. So this is very, very important, and it is a very sure question in case of your exam. Converting galvanometer into ammeter as well as converting galvanometer into voltmeter. Either of the two they will ask in board exams. Okay. So conversion of galvanometer to ammeter, first of all you will have to draw a diagram. And how is the diagram? You have a connection, that is a circuit diagram, wherein you have the presence of the galvanometer G and it moves in this way. So there is one extension, that is a parallelly connected resistor, and you have this form. Okay. So the complete setup is covered by these dotted lines. Okay. And there is a flow of current I. Students, whenever there is a flow of current, think the current is flowing in one single pipe. Sudden a pipe has got two divisions. Two other pipe is connected. Two other canals is present over there. Is it that the water flows only through one canal? No. It occupies two other canals as well. Some of the water flows from the one canal. Some of the water flows from the other canal. That is, it divides itself. Similar thing acts here also. That is, the current is moving over here. As it comes here, it has got the junction where it flows. Some of the current flows downwards and some of the current flows towards the galvanometer. So towards the galvanometer, you call it as Ig, the current through the galvanometer, and towards the resistor. So this resistor, call it as S because it is called as shunt resistor. So now, when I passes here, it is from the total amount you are minusing, that is subtracting the current which is flowing through the galvanometer. So subtraction of the total current with respect to the current which is flowing through the galvanometer gives you the amount of current which is flowing through this resistor. This is called as a shunt resistance. Okay, shunt resistance. So, concept you have to remember, conversion of galvanometer to ammeter is done by connecting a shunt resistance or the low resistance which is called as a shunt resistance in parallel with respect to the galvanometer. In parallel with respect to galvanometer, we are connecting a resistance, that is a low resistance, call it as a shunt resistance, and because of which you will be getting the complete setup as ammeter. This is proved experimentally in your laboratories. You can even check out how exactly the connections are made when you go on with your practicals. Okay, so this is the concept. Having this concept, we know that according to Ohm's law, we have V is equal to I and R, I into R. Okay, this is due to the Ohm's law. Okay, so that potential difference across the two ends is directly proportional to current which is flowing through the conductor. When you remove the proportionality constant and put equal sign, R becomes the proportionality constant over here. So when you have this case, having the same thing, we are going to check out for the potential difference across it. So potential difference across G is equal to potential difference across, yes, that is the shunt resistance. Okay, so there are two resistance, G as well as S. So potential difference here in case of galvanometer and near to shunt resistance. What is the potential difference? Potential means V. So V is equal to IR. So through galvanometer, what is the current which is flowing? IG. And what is the resistance? Because according to Ohm's law, you have V is equal to IR. R is what? R is nothing but G itself. Okay. So next you have potential across S. Across S, you have current as I minus Ig and the shunt resistance is nothing but S itself. So you are calculating for Ig. So retain your S here. So now Ig divided by I minus Ig. This is the value for you to check on the shunt resistance. So when you calculate for IgG divided by I minus Ig, you will get certain value, and that value is said to be low resistance value. That value's resistance you're supposed to place over here parallel to the galvanometer. That is when you convert galvanometer to ammeter. So next your work is to just take up I minus Ig into S is equal to IgG. So I into S minus IGS is equal to IgG. Retain IS, take all Ig family to one side plus IGS. Take Ig as common, so you will have G plus S and you have I into S here. So now you will have S divided by G plus S into I, which is equal to Ig. So having this is the final answer. Having this, you can say that the current through the galvanometer is directly proportional to the current. So Ig is directly proportional to I is the concept over here. So I hope you understood how you conversion of galvanometer. How do you go through with the conversion of galvanometer to ammeter? The only one main important thing what you have to remember is the connection is with respect to low resistance, and that low resistance is called as shunt resistance, which is connected parallel to the galvanometer. That is all about this conversion of galvanometer to ammeter. Similar way, you have conversion of galvanometer to voltmeter. But here, it is not the parallel connection, it is the series connection. And here, the series connection is with higher resistance and not lower resistance. So, two differences are there with respect to converting galvanometer to ammeter with respect to converting galvanometer to voltmeter. In ammeter, you connect low resistance called as shunt resistance parallelly to the galvanometer. But in voltmeter, you connect the resistance in series with the galvanometer, and that resistance is said to be very high. Okay. Here you are calculating the conversion of galvanometer to voltmeter, that is by this circuit diagram. So you have a current, a circuit through which the current I is passing, and you have a connection of galvanometer which is connected in series with the actual resistance R, and this is enclosed here. Actually, this is the main setup and through which the current is flowing. So now you will have, so the current flowing here is said to be Ig. So now according to Ohm's law, we have V potential is equal to Ig into G plus R, because we have two resistance in connection with each other. So in order to know the resistance R, it is nothing but V is equal to G plus R divided by Ig, and V by Ig minus G gives you the value of R. Then we will get to know what is that value of R in ohms we are supposed to connect in series with it. So we'll get the value of, that is the maximum value, high value of R over here. Then we know that by this equation we can say that V is equal to Ig into G plus R. By this equation itself we can say that V is directly proportional to Ig. Okay, so that is the potential is directly proportional to the current which is flowing through the galvanometer. That is how you can say that converting galvanometer is completely to voltmeter. So that is all about this concept, and this is also very important question with respect to your board exam. So in today's class we have discussed about the magnetic dipole moment, that is a Bohr magneton of the electron which is revolving around the positively charged nucleus, and moving coil galvanometer means what, and the conversion of galvanometers to ammeter and voltmeter concepts. That is, today's session is very important, that you will have to understand the session 5 of this chapter very well, which is very important in terms of your examinations. Let us all meet in our next session with the upcoming chapters. Until then, have a good day. Thank you.